we'll finish our submodule on modeling with functions with a really great topic. We're going to look at modeling with exponential functions. This is very useful for situations in which you know that something changes by, say, doubling each time or tripling each time. So let's start by recalling what plots of exponential functions look like. The function, if I call f of x a to the x, then what does this look like? So I have my output f of x here, my input x. So I know at 0, my value is 1, and then I blow up very rapidly this way, and I decay towards 0 this way. So you can see that this is really characterized by rapid growth. In particular, if you think that a is equal to, say, 2, then I'm essentially doubling each time x is increased by 1. So I start, for example, at x equals 0, and I get the value 1. When I plug in 1, I double that to 2. When I plug in 2, I double it to 4, 3, 8, and so on. So when are exponential functions good for modeling something? Well, it depends on the types of things you're talking about, as is always the case with modeling. There's no hard and fast rule. You really have to read the question and decide if what it's telling you indicative of an exponential function. Things that commonly fall into this are biological things, where perhaps some population of a biological organism is known to increase at an exponential rate. This is particularly true for sort of very simple biological organisms, cells, bacteria, viruses, things that don't take very much time to grow. So let's look at a classic example here. Let's say we have a colony of bacteria. Sounds like fun. Let's say it starts with 10 members. So I begin with 10 bacteria. And I know that every hour, the amount of bacteria double. So suppose the population doubles every hour. And our goal is to write the population p as a function of t, i.e. write the number of bacteria as a function of time in hours. Now, I know that from the problem, the population doubles every hour. So this is your hint that you should be thinking about an exponential function. I want to be starting at something, and then boom, after one time unit, I've doubled. After another one, I've doubled again. So the hint tells us that somewhere in the problem, I'm going to get 2 to the t. And this accounts for the doubling property. It would be nice if we were done, but there is one more thing we have to account for. This, if I just return to you this as the answer, there's a major problem, which is that it doesn't tell me how many bacteria I start with. Because if I plug in t equals 0 here, I get 2 to the 0, which is 1. Now, that's inconsistent with starting with 10 members. This would seem to suggest I start with 1 bacteria. So we have to multiply this by 10. And this compensates for the inadequacy of the 2 to the t alone by saying, well, I start with 10 and then I start doing this doubling property. So this is referring to the starting population. I'll just make a remark that this type of analysis carries over to more general situations where you have some starting population and some rate of expansion. So something like P of t equals, let's say, P0, your starting population, times a to the t, where a is, the rate of growth. So are you doubling? Are you tripling? Are you moving at a factor of 2.5? This is a very flexible model in that regard. So how do you know, again, whether you should use the exponential model or not? There's no hard and fast rule. You need to look at the problem. And the hint for us was the assumption that the population doubles every hour. This was the major hint that we should be using an exponential model, in particular with the bases too.